Good afternoon, everyone. I'm Pratik from IIT Bombay, and in the next 15 minutes, I'll talk to you about our paper on the importance of shape adaptation in hand tracking. Let's briefly understand what the problem of hand tracking is in our context. Consider we have a depth camera observing the motion of a user's hand. The goal of hand tracking is to reconstruct a 3D hand model that resembles the geometry of the user's hand in each frame of the video. Now, to simplify, let's decompose this geometry into two components, shape and pose. The shape captures the user-specific identity, for example, size, finger length, thickness, whereas the pose captures the configuration of the skeleton. This is generally represented by angles at each joint in the skeleton. The state-of-the-art approaches until now can track most poses of the hand which says that the shape lies close to some training set of shapes. However, they suffer when tracking unseen hand shapes, which lie out very far away from this set. We present the first method that can track such hands with a wide range of hand sizes. Our key idea is to introduce local scale adaptation to the mesh. We estimate this local scale automatically from the depth image of the user. We also present an efficient method to integrate our local scale parameters into scaling transformations. Our idea of local scale adaptation can be used for even full body human meshes or rather any articulated objects. Before explaining our idea in detail, let's look at the current state of the art. Inspired by recent literature on human body, face, shape, and hands, we use a parametric shape model, which decomposes the parameters into shape and pose. We use the most widely used state-of-the-art hand model, Mano. It's an articulated hand model with shape and pose blends. It is learned from 31 subjects, mostly adults. Let's look at the process of obtaining a new hand shape given the template mesh and the shape parameters. The shape parameters are used to adapt the template mesh to a user-specific hand shape. This is done by adding offset vectors, also called as shape blends, to each vertex. These shape blend offsets are obtained by linear combination of PCA bases, which are computed from the rest pose registrations of the training set. The parameter beta here controls the weight of each of the basis vectors and thus controls the shape. Here are a few shapes obtained by varying the shape parameters close to the mean. Now, okay, let's do an experiment. Let's vary the shape parameter away from the mean. The first few parameters generally represent maximum variance. And so let's increment this shape, these parameters away from the mean and let the other parameters vary around the mean. We can see that as the shape parameters go away from the mean, the shape degrades. This is because the linear PCA basis is not enough to reconstruct these hand shapes with substantially different deviations. Here are two examples, one adult and one child. The child's hand is not present in the training shapes and is far away from the adult hand shapes which are present in the training set. As a result, existing hand shape models cannot fit to adult hand shapes, but can fit to adult hand shapes, but not to child's hand. Here, the white region shows where the model fits on the depth image correctly, and the red and blue regions denote mismatches. We tackle this problem by introducing local scale adaptation to Mano. Specifically, we define a scale parameter corresponding to each bone of the hand, thus giving us a local control for each bone of the hand, and we can obtain this scale by dividing the bone length of the user by the bone length of the template hand mesh. We call our new shape model adaptive Mano, or in short, A-Mano. These intuitive local scale parameters enable us to explicitly control the size of the hand. And also, if we note that our local scale parameters sort of are complementary to the existing shape parameters in Mano. So in other words, we can say that A-Mano augments the shape space of Mano, and as a result, we have an overall larger shape span. Okay, now let's see if there is a slight problem if we directly use these local scale parameters in the linear blend scaling model, like any kind of geometric scaling. So here is what a typical LBS equation looks like on the left. And one way to incorporate our local scale parameters in this equation would be to directly anisotropically scale the bone along the reference frame. In this case, we add the parameter phi j, which is our scaling factor along that bone. But we notice that phi j is constant over the mesh. So if a vertex lies beyond the bone endpoints, it will get overly scaled. And this effect is not removed by bone weights alone. And when multiple bones deform an area around the common joint, it results in unwanted bulges. So here is an observation. We can avoid this problem if we know the position of a vertex with respect to the bone's endpoints. We can then restrict this effect of scaling to part of the mesh that is associated with just that particular bone. So similar to traditional bone weights, we use an additional weight matrix called endpoint weights that capture this information. We compute these endpoint weights by minimizing a shape-aware Laplacian subject to some bone endpoint constraints. More details about this can be found in the paper. I'll move ahead with this. So if we use these parameters, so the scaling factor along with our endpoint weights, this gives us a way to elegantly integrate our local scale parameters into the modified LBS. And now we can notice that we can scale the desired bone and deform it without any bulging or scaling artifacts during deformation. So okay, now we have this machinery and of adapting local scale of the mesh. So let's revisit this example of a child's hand, and the explicit local control that we now have enables us to fit our model more accurately to a child's hand. So we see less red and blue regions, and the shape mesh has been adapted to the user's hand very nicely. Okay, so far so good. So now let's focus our attention on how we can fit this our A-mano mesh to a depth image, and further even track it to a sequence of images. I'll briefly outline our framework. We apply a hand pose estimation network on the first depth image of the user to obtain the joint positions from which we can calculate bone length of the user, which in turn allows us to calculate our local scale parameters corresponding to the user's hand. The next stage is the shape calibration, in which we optimize the shape and pose by registering locally scaled A-mano on the first few frames. And once the shape parameter converges, we optimize only the pose parameters on the subsequent frames. We call this as a tracking stage. Now we optimize the shape and pose parameters in our calibration and tracking stages by registering the mesh to the observed data. Now let's discuss our registration process. We use an energy minimization framework to optimize the model parameters. Our energy is a weighted combination of multiple terms. The 3D and 2D data terms ensure that the model explains the observed data. The bound and PCA pose prior terms that ensure that the pose remains kinematically valid. The intersection terms, which is E and show, is used to penalize finger penetrations using a set of proxy spheres on the fingers, whereas and this enables realistic deformations. We don't have any spheres on the palm because the angle limits take care of that. Now we use a E-init term, which is the re-init term, which is used to recover from tracking failures. So the way we do it is we detect fingertips in each frame using a hand pose estimation method, and ensure that the model's fingertips are close to the detected fingertips. We also have a shape prior term, which says that okay, the hand shape should not deviate too far away from human hand. So basically, should not go too far away from the mean shape. And all these terms so far that we have seen are per frame terms. So we also have one more term which says that the tracking should be smooth. So we also have a temporal prior on that. And we linearize each of these terms and then use a Levenberg-Marquardt algorithm to optimize their energy. More details about all the other terms can be found in the paper. I'll now focus on the 3D and 2D data terms, which play a crucial role in the registration, and also the effect of the shape adaptation on these terms. The 3D data term minimizes the distance between the observed point cloud and the model. We use the point-to-plane iterated closest point, or in short ICP, due to its faster convergence. In this case, for each observed point xi, we need to compute the closest point on the mesh, yi. Let's consider two scenarios. In one case, we have a model without the local scale, and in the other, we have a model with the local scale adaptation. We can see that the computed closest point correspondences are incorrect in the first case because of the difference in the local scale of the model and the user's hand. And this error, and as a result, what happens is the ICP does not converge correctly. And this error is further propagated as we track across frames, and as a result, there is no, the tracking fails. Whereas if we have a local scale adaptation, these correspondences are reasonably better, and thus ICP convergence is better, and thus we can achieve better tracking. Similarly, let's look at the 2D data term. This penalizes the projection of the model outside the silhouette of the depth image. Considering our earlier two scenarios, we observed similar pattern here. That is, the correspondences are incorrect when the model is not adapted to the user's hand shape, and ICP fails, whereas it works better when the shape resembles that of the user's shape. Now, this reinforces the fact that a user-specific hand model is necessary for accurate tracking, and our local scale adaptation is one way to achieve this. Here is an example of a child sequence. Here we can see that existing hand models fails to track because of incorrect correspondences, whereas our model can track child's hand more accurately because of its ability to adapt its shape to the users based on the depth image. We evaluate our method on the HANDS 2019 challenge dataset, which is the most challenging publicly available hand pose dataset. We use three metrics, two dense and one sparse. The sparse metric that we use is the key point error, which measures the Euclidean distance between ground truth key points and model key points. And the dense metrics, we use a data to model error and a model to data error. The data to model error, E3D, measures the 3D Euclidean distance between the observed point cloud and the mesh. And the model to data error, E2D, measures the pixel distance of the model from the observed silhouette, projected model from the observed silhouette. And our method outperforms the best method that has been provided by the challenge organizers. So then let's look at our tracking results on publicly available data sets in terms of tracking. Since our model consists of only the hand mesh, we crop out the background region and the wrist region. In the guest 2 data set, the user wears a wristband, and which we use to crop out the hand region for tracking. In cases where we don't have a RGB mesh, we just use the depth image and crop out a bounding box that is closest to the camera. Our method can perform in real time. We also evaluate our method on the big hand dataset, which is the largest dataset available from multiple viewpoints. And we can see that our method works. It's robust enough for a variety of viewpoints, even the ego view. Our method is robust enough for complex poses as shown in this MSRA dataset. And our method is also robust to noisy depth data that is acquired from a Kinect camera. In this case, this is the NYU dataset, which was the first dataset which was annotated hand pose dataset. To conclude, here is the key takeaway from the talk, that shape adaptation is essential for accurate hand tracking, and we present that decomposing local scale and shape blends provides more control over the shape. Thank you, and I'll be happy to answer any questions that you may
have. Thank you very much for this talk. Are there any questions?
I have one question. One of the advantages that you get from using a model gives you bounds in the parametric space within which you sample within this within specific domain, you can get possible shapes in the output. I'm wondering, how does this extend to the scale, global scale parameters that you use in manual? How do you make sure that this gives you hand shapes that are still anatomically correct in some cases?
Yeah, so what happens is our parameters are, as you said, that shape parameters in parametric models, you cannot deviate too far away from those parameters. That gives us some control. But how do you go beyond that? So you need to have some domain knowledge of the model. In this case, we use local scale parameters. And this is basically a complementary way of adapting the shape, which is, so we still use those parametric models, but how we can leverage and go beyond that such that we are in that space of good hand shapes. So the proper way, probably the way forward on this would be to also have a prior on the local scale parameters, which will also ensure that all the local scaling that you are doing are ensuring that, this follows particular human hands. Like, because not every scale can be independently, every bone can be independently scaled. If one finger is scaling, then the other finger should also be scaled accordingly. So we can have some prior on that, and that will definitely.
Thanks. Maybe one more question. How does this compare with having a global scale parameter for the whole hand?
Yeah, so the dataset organizers that I showed, so they have a local global scale parameter, but that does not capture all the things. So global scale does help. So global scale plus local scale is like the best thing.
Okay. Any other questions? So I would have another question. So would this model be able to adapt to, say, non-traditional actions? Like if somebody had an injury and half finger is missing, could it just scale by 0 and then it would work? Or?
Yes, it will definitely work.
So did you try it? I mean,
yeah. So we did try generating very small hand shape.
right.
But we didn't do it 0, but we like have some examples where one of the fingers is scaled very low, because like, this is very mathematically elegant. So you can explicitly have that parameter to 0 and then it's just go down. There are some cases where the finger's thickness blows up. So maybe we'll have to have some control on the thickness of the fingers. If we can reduce the radius also, because right now if you squash it, it just spreads. So maybe you can also reduce the radius. That will probably.
Right. Thank you. Okay, then we are moving on with the next paper. So the next paper is type restorative maps for tracking detailed liquid surfaces by Fumiya Narita and Ryoichi.